Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss the priority interrupter. So, the digital computer system, mainly it consists of the central processing unit, memory subsystem, and I/O subsystem. So, these are the three main essential components of the computer. So, the CPU, it performs various operations, and the memory. So, memory is used to store some programs as well as the data associated with that programs, and I/O subsystem. So, this I/O subsystem, it provides efficient communication of the CPU with the external world, because we are interfacing several I/O devices with the CPU, so that the CPU can communicate with the outside world. Okay, so here, see, we are discussing about the priority interrupter. So, what is priority interrupter? So, priority interrupt is a mechanism that allows the highest priority device to interrupt the CPU. So, that is called priority interrupter. So, the data transfer between the CPU and the I/O device is initiated by the CPU. So, when we have connected several I/O devices with the CPU, so there is a data transfer between the CPU and the I/O devices. So, this data transfer will be initiated by the CPU, central processing unit, and the CPU cannot start the transfer unless the device is ready to communicate with the CPU. So, the CPU it cannot start the data transfer unless the I/O device is ready to communicate with the CPU. So, the readiness of the device can be determined from an interrupt signal. So, we can determine this readiness of the I/O device with the help of the interrupt signal. Okay, so whenever the I/O device is ready to communicate with the CPU, then the I/O device will send in one interrupt signal to the CPU, so that the CPU will involve in the operation. So, in that way, using the interrupter, so we are initiating the data transfer between the CPU and the I/O devices. So, we have different data transfer modes are there. So, that are first one is a programmed I/O. So, basically we have three types of data transfer modes. So, in that, the first one is a programmed I/O, and second one is a interrupt initiated I/O data transfer. Third one is a direct memory access. So, what is programmed I/O? Programmed I/O is the data transfer will be initiated by executing I/O instructions of the program. So, in the program, we have some input and output related instructions, like in and out. So, these are the instructions which are related to read or write the data into the I/O devices. So, whenever these type of instructions are executed, then the data transfer will be initiated. So, that is called programmed I/O. Programmed I/O. So, we can see in detail about the programmed I/O. So, this is a scenario of this is a CPU, and this is an interface, and this is a I/O devices. So, as we know, the I/O device we cannot connect directly with the CPU, because there are some differences that exists between the central processing unit and the I/O device. So, we have some differences. That differences are nature of behavior of the CPU and I/O device, and the data transfer rate, and the data format, and the operating mode. So, like that, we have some differences between the central processing unit and the I/O device. So, in order to resolve those differences in between the CPU and the I/O device, we are using a one interface circuit. one circuit that is called interface circuit. Okay. So in the programmed I/O, when the I/O device is ready to transfer the data, then it places a data in the I/O bus. After that, it will send a data valid signal to the interface, so that the data which is available in the I/O bus will be placed in the data register, because the interface, it mainly consists of two types of registers. One is the data register and another one is the status register. So these are the registers associated with the interface circuit. So the data which is placed in I/O bus will be stored in the data register. So initially the flag bit will be equal to 0. That means it will be set to logic 0. Okay. So whenever the data is loaded into the data register, then the status bit or status register, that is, will become F is equal to 1. So F is equal to 1, it indicates that whenever the status register F is equal to 1, then the CPU will read the data from the data register through the data bus. Okay. So whenever the data is loaded, with the data register, then the interface will send a data accepted signal to the I/O device. Okay. So in this way, we can transfer the data from the I/O device to the CPU by executing some I/O instructions, I/O instructions. Okay. So, and also here, see here. So data bus, the data bus is used to read the data from the device. Okay. And also the data bus can be used to send the data to the device. Okay. And address bus. So address bus, it is used to identify the address, identify the I/O device using the address, because several I/O devices we are connecting with the CPU. So the CPU can identify the different I/O devices using their address. So that address information will be placed in the address bus, so that the particular I/O devices will be selected. And here you can see two types of operations are there associated with the I/O device. One is the I/O read and another one is the I/O write. So these two are related to the I/O operations. So that means, suppose if you have any I/O device, for that device we can perform two operations, either I/O read operation or I/O write operation. So these are the two operations we can perform with the I/O devices. So whenever we are reading the data, then we can use the I/O read operation, and whenever we are writing the data to the I/O device, then we can perform the I/O write operation. So this is a programmed I/O data transfer. But the main drawback with this data transfer method is, so here the CPU, it has to continuously check the status register. So it has to continuously check the I/O device, whether the I/O device is ready to transfer or ready to communicate with the CPU or not. So the CPU has to spend more time on checking this status register or flag bit. So that means some considerable amount of CPU's time is wasting here. Okay, so this is a drawback in the programmed I/O data transfer. Okay, so to overcome this drawback, we are going for the second type of method, that is called interrupt initiated I/O. So what is interrupt initiated I/O? So whenever the I/O device is ready to transfer, or whenever the I/O device is ready to communicate with the CPU, then the CPU, the interface, so the interface will send one interrupt signal to the CPU. Okay, so before receiving the interrupt signal by the CPU is busy with executing its important programs. Whenever the CPU receives interrupt signal, then the CPU will stops currently executing program or currently executing task, and then it stores the return address in the stack memory. Then the program control, the CPU's program control will be transferred to the interrupt service routine program. So that is a interrupt initiated IO. So that means here only the CPU will involve in the data transfer whenever it receives a interrupt signal. Otherwise, the CPU will be busy with executing its important programs. So the number of IO devices attached to the computer. Several sources will request service simultaneously. So to the computer or CPU, we are not connecting only a single device. We are connecting several devices like some keyboard, mouse, some other memory card. So like that, different IO devices we are connecting. So there may be a chance that all the several IO devices may raise a request a service request to the CPU simultaneously. So the first task of the interrupt system is to identify the source of interrupt and then decide which device to service first. So whenever suppose if multiple interrupts are raised simultaneously to the CPU, so the interrupt system first it decide what will be the source of the interrupt. So that means from which device the interrupt occurred, from the keyboard or mouse or some any other memory device. So like that, the first interrupt system first it has to decide what will be the source of the interrupt. After that, it has to determine which interrupt has to be serviced first. So that means always the interrupt with the highest priority will be serviced first, then the lowest priority. So like that, all the interrupts will be serviced in a interrupt system. The priority interrupt is a mechanism. So it is a mechanism to determine which interrupt is to be serviced first when two or more requests are made simultaneously. So also determines which interrupts are permitted to interrupt the computer while another is being serviced. So only certain type of interrupts are allowed to interrupt the CPU, not for all. So like that also we have to service. And higher priority interrupts can make requests while servicing a lowest priority interrupts. So always the highest priority interrupt will be serviced first. So see here, suppose you have a CPU and let's assume some three devices are interrupted simultaneously with the CPU. So let's assume 0, 1, 2. So 0 is the highest priority and 2 is the lowest priority. Okay. So suppose let's assume currently the lowest priority interrupt is servicing. So when the lowest priority interrupt is servicing by the CPU, suddenly at some point of time the highest priority interrupt occurred to the CPU. Okay, so that the CPU will stops the executing the lowest priority interrupt and the highest priority interrupt will be serviced because always it is the 0. So it is 0 is the highest priority. So that's why always the CPU will service the highest priority tasks first. So in this way, all the priorities will be serviced. So this priority interrupts can be implemented using two approaches. The first one is the software. It is also called polling the devices. And the second one is the hardware. So these are the two approaches. One is the software, also called polling, and the second one is the hardware. So first one. So let's see first one. So priority interrupt by software. So the priority is established by the order of polling the devices. Okay. So that means here, suppose if the two or more devices raised a interrupt. So first we need to check one device. Suppose if the device is not raised the interrupt, then it checks the second device. second device also not raised the interrupt request, then we are checking the third device. So like that, all the devices we are checking. So this process is called polling. Okay. So priority is established by the order of polling the devices. Okay. And second one is flexible, since it is established by software. Okay, it is a flexible because only we need to modify the program. So that's enough. Next, low cost, since it needs very little hardware, because it is a very low cost, because here we are not using that much hardware. Okay, because the cost is directly proportional to the more hardware. As the hardware increases, the cost of the system also increases, but not here, because this priority interrupt is implemented by using the software. So that's why we need less hardware, and it is a slow, very slow, because here in this process we need to check all the devices to determine which device is raised the interrupt request. Okay, so this is so the drawback of the polling. So what is the drawback of this polling? So the CPU, it takes more time to check which device has generated the interrupt signal, but it takes less time to execute the interrupt service routine program. Okay, so see here. So suppose if you have a 4 devices. So this is device 1, device 2, device 3, device 4. So in polling, what we are doing? So first we are checking the first device, whether the first device is generated the interrupt or not. Suppose if the first device is not generated the interrupt, then we are checking second device. Second device also not generated interrupt, we are checking third, next fourth, so on so on. We are checking all the devices. So suppose if the fourth device, so if you mention the priority of the devices, so the priority of the first device is 0, next 1, next 2, 3. So that means the device 1 is having the highest priority and the device 4 is having the lowest priority. So when the device 4, that means when the lowest priority device interrupt is occurred. So in order to determine the lowest priority, it takes more time because it is a lowest priority interrupter. So in order to determine this, it takes more time because first we need to check the highest priority. If it is not done, then second, then third, next fourth. So now this raised the interrupter. Let us assume this fourth device raised the interrupt request. So it takes more time. It takes some time to check all the devices. So that's why here it is very slow process. And so that is a drawback. So the CPU takes more time. So it is taking more time to check which device has generated the interrupt signal. But it takes less time to execute the corresponding ISR program, because the ISR program, the time required to execute the ISR program is fixed for all the devices. But here the time required to determine which device generated the interrupt is more than the time required to execute the ISR program. So that's why it is this is a drawback of this software. So in order to overcome this problem in the software interrupt, then we are going for the hardware. Okay, so priority interrupt by hardware. So here in the priority interrupt by hardware, we have two methods. Okay, two approaches are there. One is a daisy chaining and another one is a parallel priority encoder. So using these two methods, then we can overcome the drawback what we have faced in the software interrupt. So require a priority interrupt manager which accepts all interrupt requests to determine the highest priority request. First, since identification of the highest priority interrupt request is identified by hardware. Each interrupt source has its own interrupt vector to access directly to its own service routine. So the hardware priority function can be established by either serial or the parallel connection of the interrupt lines. So the serial connection is also known as the daisy chaining method. So this is a daisy chaining method. So this is the first method of the hardware interrupt by hardware, interrupt priority interrupt by hardware. So what is daisy chaining? So the daisy chaining method of establishing priority consists of serial connections of all the devices that require that request an interrupter. So here we are connecting several devices. So all the devices we are connecting in a serial manner. That means serial manner means one after another. So the output of one device we are connecting to the input of the second device. Similarly, the output of the second device we are connecting to the input of the third device. So like that, all the devices are connected in a serial fashion. So that is called daisy chaining priority. So here you can see we have a CPU, and here for the simplicity we have taken the three devices: device 1, device 2 and device 3. Okay. So suppose you see, suppose if the device 1 is requested, is generated the request, interrupt request, then this line will be active. This line will be active. That means the interrupt from the first device will be given to the CPU, so that the CPU will send an acknowledgement to the interrupting device. Okay. So the every device here, it is having priority input and priority output. So one input and one output. So priority input and priority output. So whenever the first device is it receives a interrupt acknowledgement from the CPU, then the first device will generate a vectored address. Vectored address. So vectored address means so the device, it is having a interrupt service routing program at a fixed addresses, at a fixed address. Okay, so that is called vectored address 1. So that this vectored address 1 will be given to the CPU in order to execute that ISR program. So in this way, all the devices can be all different multiple interrupts will be serviced by the CPU. Next, suppose if the second device request generated the interrupt, then this interrupt, so this line will be active. Okay. So suppose if the first device is not generated the request, so that what will happen? So the first device is not generated request, so that the output, the priority output signal will be given to the priority input of the second device. Suppose if the second device generated the interrupt request, then the second device will send a interrupt to the CPU. Then CPU will give the acknowledgement. Okay. After that, the device 2 will generate a vectored address that will be given to the CPU in order to execute the corresponding ISR program. Okay. So this is a daisy chaining priority method. And coming to the second type of the priority interrupt by hardware is the parallel priority interrupt. Parallel priority. So the parallel priority interrupt method uses a register whose bits are set separately by the interrupt signal from each device. Priority is established according to the position of the bits in the register. In addition to the interrupt register, the circuit may include the mask register, whose purpose is to control the status of each interrupt request. The mask register can be programmed to disable low priority interrupts while the high priority device is being serviced. It can also provide a facility that allows a highest priority device to interrupt the CPU while the lowest priority device is being serviced. So always the highest priority the priority device needs to be serviced, while the lowest priority device is being serviced. Okay, so you can understand this with this diagram. So the priority logic for system for 4 interrupt sources. So here we are connecting 4 interrupting sources. We are connecting 4. One is the disk, and the second one is the printer, reader, and keyboard. So these are the 4 devices, IO devices. So that we are connecting. So see here. So we are using one 4x2 priority encoder. Priority encoder. So what is priority encoder? So priority encoder is always it gives the highest priority to service. Okay. So this is a interrupt register. So since we are using 4 devices, it is a 4-bit interrupt register. So we are connecting only the 4 devices. So that is okay. So this is a disk, printer, reader, keyboard. And the interrupts, the priority of the disk is 0, and the priority of the printer is 1, and the priority of the reader is 2, and the priority of the keyboard is 3. So the 0 it indicates highest priority, and 3 it indicates lowest priority. Okay, so these interrupt registers are connected to the AND gate, connected to the priority encoder through the AND gate. So AND gate is a 2 input. So for every AND gate, one input. So one input is from the interrupt register, and another input is from the mask register. Okay, mask register. So mask register also, the size of the mask register is equal to the number of devices that we are connected. So here how many devices we have connected? 4 devices we have connected. So the size of the mask register is 4. So 0, 1, 2, 3. So like that we have given the connections, and the outputs of all the AND gates we are giving to the inputs of the 4x2 priority encoder. So the output of the first AND gate we have given to the I0, and output of the second gate we have given to the I1 of priority encoder, and the third AND gate output we have given to the I2 of priority encoder, and fourth output of the fourth AND gate we have given to the I3 of priority encoder. Okay, and we have some 3 outputs are there. Okay, so 2 outputs. One is X, and another one is a Y, and one more output, that is a IST, interrupt status. Okay. So the outputs X and Y. So the output X and Y, it depends upon the input signals of the priority encoder. So you can understand this with the some truth table. So let's see inputs. So what are the inputs? I0, I1, I2, I3. So these are the inputs. Suppose if the first device generated the interrupt request. So first device. So what is the first device? Disk. So what is the priority of the disk? 0. That means highest priority. So highest priority. So that the disk is okay. So whenever the corresponding device is raised the request, then in the interrupt register logic 1 will be stored. So in this scenario, disk 1 generated the interrupt request. So 1 will be stored in the interrupt register, and the remaining devices are not generated the interrupt request. So that's why the remaining registers it will store 0. So that means here one of the input to the AND gate, first AND gate is 1, and mask register. So mask register always it stores all or ones. All registers are stored with 1. So here the input to the 1, and the remaining all are So see here. So this is 0, 0, 0, 1, 1, 1. So what will be the output of the AND gates? So here it is 1. Here 0, 0, 0. Okay. So that means see here. So first device it generated the interrupt request. So that's why you will get the output as a 0, 0, 0, 0. X is equal to 0, Y is equal to 0. Okay. So because here when the first device, when the highest priority device it generated the interrupt, no need to check the remaining devices because already the highest priority device it generated the request. So always the highest priority device will be serviced first. So that's why the remaining devices no need to check. So that's why the remaining states will be represented with a D or X. We can represent it with a D or X. So D means don't care. X means don't care. Okay. So the corresponding outputs are X and Y 0, 0. So when the interrupt is generated, then the IST flag will be set to 1. Okay. So that is the first. And consider the second device. Suppose the second device generated the interrupt. So that means the corresponding interrupt register will be set to logic 1 and the remaining devices will be set to logic 0. So now the output of the second AND gate. Consider. Okay. So now, so see here. So here 1. So the output of the second gate will be 1 and the first gate will be 0. So the first device. Okay. Means second here. So this is first, this is second, third, fourth. So second device it generated a interrupt. So what will be the corresponding output? 0, 1. For third device 1, 0. For fourth device 1, 1. So whenever the interrupt is occurred, then the corresponding IST bits will be set to 1. Suppose if the no device is generated the interrupt, then the outputs will be DD. That means don't care. If no device is generated interrupt, then the interrupts will be 0. All inputs will be 0. So that the output will be don't care and the corresponding IST bit will be set to 0 because it indicates that no interrupt generated. Okay. Okay. So suppose if all interrupts, all devices they raised an interrupt simultaneously. So device 1 also generated, device 2 also, 3 also, 4 also. All devices raised a interrupt. So the priority. So first, when multiple interrupts are there, we have to check the priority first. So first device disk is having the priority 0. So 0 means highest priority. So the first device will be serviced first. After that, the second device will be serviced. Next third, next fourth. So in this way, based on the priority, all the devices will be serviced by the CPU. So suppose if the first interrupt is generated, the corresponding XY bits are 0, 0. So this is a vectored address. So in that vectored address, the corresponding ISR program will be there. What is the first device? Disk. So for the disk device, the corresponding interrupt service routing program is located at the address all zeros. Similarly, if you consider a printer, so what will be the output of the printer? X is equal to 0, Y is equal to 1. So X is equal to 0, Y is equal to 1. So that means 1, 0, 0, 0, 0 like that. So in that address, there is the ISR program corresponding associated with the printer. Okay, so that is a vector address to the CPU. And here see, this is IST bit and this is an interrupt enable. So this is a logic circuit for generating the interrupt to the CPU. So when interrupt is occurred, IST will be 1. So this will be 1 and this will be 1. When interrupts are enabled, so interrupts are enabled means equal to 1. So this will be 1 and this will be also 1. So enable. Okay. So see here. So interrupt is generated. So for this AND gate, the inputs are 1 and 1. So that the output of the AND gate will be 1. That means interrupt to the CPU. And whenever the CPU it receives an interrupt, then the CPU will send an acknowledgement. Okay. So that again it will enable. So this vector address will be sent to the CPU. So in this way, the priority will be serviced. And priority encoder are truth table. So we have seen the inputs truth table, outputs, and the Boolean function. So Boolean function, when you apply a k-map for this, then you will get x is equal to I0 dash into I1 dash. Similarly, when you apply k-map for this y, you will get I0 bar I1 plus I0 bar I2 bar. Similarly, when you apply this, so IST is equal to I0 plus I1 plus I2 plus I3. So in this lecture, we have discussed about what is interrupt and the different priority interrupt sources and the different methods for generating the priority interrupt. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.